Hey everyone, today let's solve one of those interview puzzles that look simple but quickly twist your brain. Duplicate zeros in an array. We will go step by step and understand how to do it efficiently without using any extra space. Alright, here is our challenge. We are given an array, let's say 10230450. Our task to duplicate every zero in this array. Sounds simple, right? But here is the twist. The array's length cannot change. So every time we add a new zero, something else must shift to the right. Now let's think. If we duplicate the first zero, what happens to the rest of the numbers? Will they all fit inside the same array, or will something get lost along the way? That's what makes this problem interesting. We have to transform the array in place without using any extra space. So let's explore how to do that calmly and step by step. This problem shows up a lot in coding interviews, especially with companies like Amazon, Google, and Microsoft. It's not just about duplicating zeros, it's about thinking through how data shifts inside memory. You will see the same kind of thinking applied in real world systems, like when we handle live data streams or work with pixel buffers in image editing. So, if you can master this one calmly, you are building real confidence with array manipulation. Let's start with the most common idea. Move from left to right, and whenever you find a zero, insert another one right after it. Seems logical, right? But as soon as you insert, the array shifts, and that shift causes you to skip the next element. So now your loop is out of sync with our data. So let's say here at index 1 we find the first zero. We will insert the duplicated zero at index 2. So from the next element onwards our array will shift. So before inserting the duplicated zero, our array length was 8. Now, after inserting the duplicated zero, our array length is 9. But our condition clearly states that we should not increase the array length. That means at the first duplicated zero insertion itself, we have to skip the last element 0. That means our array elements got changed, which we might need at later point of time. So we will end up with the wrong result. This is the classic forward iteration trap. Alright, so what if instead of inserting, we simply replace the next element whenever we find a zero? Let's say we hit the zero at index 1. We copy another zero right after it, replacing the next value, which is 2. At first it seems to work, but as soon as we move ahead, we realize the problem. We have just lost the original element that was there, because the array keeps changing while we are still looping through it. So even this forward replacement method fails. It's time to stop fighting the array and think in reverse. So here is the smart move. Instead of moving forward, we process the array backward. We will use two pointers, both starting from the end. One pointer reads the elements and the other writes them to their final positions. This way, we can safely duplicate zeros without overwriting anything. When we move backward, everything stays stable. No skipping, no confusion. Let's see this in action. Take this array 10230450. We start from the end, copying elements one by one to their correct new positions. Whenever we hit a 0, we write two zeros backward, one at the current pointer and one just before it. So, we started from the end, copied each element to the correct position, duplicate zeros to the same index and its previous index when encountered. So the final result we got is 100230004. So everything is in place and no extra memory used. Let's see this in action with a dry run. Alright, before we start the reverse loop, notice something important. 3 new boxes appear at the end of the array. Let's understand why. Our original array has 8 elements, indices 0 to 7. Now when we look through the array, we find 3 zeros in total. Each 0 needs to be duplicated, which means we need 3 extra positions to show where those duplicates will go. So visually we extend the array up to index 10. These extra boxes don't actually exist in memory. They are just a logical visualization to help us track where the final elements will end up. We are not adding space in real code. We are just simulating what would happen if we could see beyond the array boundary. Now let's look at our pointers. I starts from the last element of the original array, that's index 7. J starts from the end of the imaginary extended array, that's index 10. From here, both pointers move backward. We copy the element at position I to position j. If the element is not 0, both pointers simply move one step back. I goes to 6, j goes to 9. But when we hit a 0, we duplicate it. That means we write 1 0 at position j and another at j minus 1. Then I moves back by 1 and j moves back by 2 because we have placed 2 zeros for that one element. This backward movement continues until I reaches index 0, and when we are done, all the duplicates are placed correctly within the original array length. So those 3 extra boxes, they were simply a way to visualize the 3 duplicated zeros we planned for. No real memory expansion, just a clever trick to help us think about how the two-pointer method shifts elements safely from right to left without overwriting anything. So before looping begins, we find 3 zeros. So we imagine 3 extra boxes at the end as we discussed. I starts at index 7, the last real element, and j starts at index 10, the logical end. Now we copy backward. The element at I equal to 7 moves to j equal to 10. Since it's a 0, we duplicate it. 1 0 at index 10 and another at 10 minus 1, which is 9. Now the position of I is 6 and position of j is 8. In the step 3, currently I is at 6 and j is at 8. We copy the element 5 from index 6 to index 8. No duplication this time since it's not a 0. So after end of step 3, I is at 5 and j equal to 7. In the step 4, I is at 5 and j is at 7. We copy the element 4 to index at 7. Still no 0, both pointers step back normally. So at end of step 4, I will be at 4 and j will be at 6. At step 5, I is at index 4 and j is at index 6 and I at 4 pointing to a 0. So we will duplicate it. 1 0 goes at j equal to 6 and another will go at j minus 1, which will be 5. So I will move one step back, which will be 3, and j will move 2 steps back, which will be 4. So at end of step 5, the new indexes of I and j will be 3 and 4 respectively. In the step 6, I is at index 3 and j is at index 4. I is pointing to a 3, So copy it to j equal to 4. Pointers move back again by one step. So at end of step 6, the new pointers will be I equal to 2 and j equal to 3. At step 7, I is at 2 and j is at 3. So I value 2 will copy to j at 3 and the pointers will move back by 1. So i's new position will be at 1 and jth new position will be at 2 at end of step 7. At step 8, I is at index 1 and j is at index 2. I at 1 now points to a 0. So duplicate it to j at 2 and j minus 1 at 1. After duplicating the zeros, finally I will move to the index 0 one step back and j will move 2 steps back to index 0. So at end of step 8, i's position will be 0th index and jth position will be 0th index. At step 9, both I and j are in index 0. Now the element points to a non-zero element which is 1. So 1 will be copied to the 0th index and after that both I and j will move one step backward. So index position will be minus 1 at end of step 9. The reverse copy is complete. Every 0 is safely duplicated in place. And that's how the reverse duplication works behind the scenes. By first planning those 3 extra spaces, we give ourselves a clear visual map of where each element should finally go. Even though the actual array length never changed, our 2 pointers I and j made sure every element was handled safely. I read each original value while j wrote it to the correct final position. Whenever a 0 appeared, we simply wrote it twice and moved both pointers backward accordingly. So, the step-by-step approach is we started from end I, copy elements to target j, duplicated zeros at j and j minus 1 when encountered. Pointers move backward until start of the array. Alright, before we go further, let's think about something tricky. In our reverse approach, whenever we find a 0, we duplicate it by writing at positions j and j minus 1. But here is a question for you. What if our array starts with zeros? Say the very first or even the first 2 elements are zeros. Where would these duplicates at j and j minus 1 actually go? Would they both fit inside the array or would one get lost somewhere? Take a second to guess and then we will see exactly what happens in that edge case. So this is our input array starting with 2 zeros 0 0 1 2 3 4. Currently array length is 6 and now to accommodate the duplicated zeros we will create 2 extra boxes, so the updated array length will be 8. Now we will traverse the array from right to left and we will copy each elements one by one, and whenever we find any zeros we will just duplicate it in their respective places. So the non-zero element will be copied from ith index to jth index and the zeros will be duplicated at jth index and j minus 1th index. So whatever we discussed earlier in the previous example, we will just follow it. So in step 1 we copied 4 from 5th index to 7th index. In step 2 we copied 3 from 4th index to 6th index. So the elements 3 and 4 which got copied to 6th and 7th index are into the imaginary boxes. So these boxes are not real memory. They are just temporary overflow space that helps us visualize what would happen if the array could grow. So when an element moves into an imaginary box, it simply gets ignored. The algorithm never writes beyond the actual array size. It's like the array saying, "Thank you, I have noted your copy, but there is no room, so I will skip it gracefully." This is how our reverse logic stays safe. It processes everything but only keeps what fits within bounds. In step 3, element 2 gets copied from third index to fifth index. In step 4, element 1 gets copied from second index to fourth index. In step 5, 0 at first index will be duplicated at third index and second index, and I will move to 0 and j will move to 1. In step 6, 0 at 0th index will be duplicated at first index and 0th index, and I will move to -1 and j will also move to -1, that is array out of bound, and this is our final array 0 0 0 0 1 2. Now that we clearly understand how the reverse approach works, it's time to turn this logic into code. We will start by counting the total number of zeros in the array. That count helps us figure out how far our right pointer j should go, including all the logical duplicates. Then, just like in our animation, we will move backward using two pointers. I will read each original element and j will write it to its correct new position. If the current element is not 0, we simply copy it backward once. But when we find a 0, we write it twice. Once at position j and again at j minus 1, and then shift both pointers back. By the end of the loop, every 0 is safely duplicated and the entire array is transformed in place with 0 extra memory. Let's write that code together. Alright, before jumping into the code, let's pause for a second and see what the problem says. Given a fixed length integer array ARR, duplicate each occurrence of 0, shifting the remaining elements to the right. So whatever we discussed during our dry run or our edge case, that's what the problem is asking for. So the input here is 10230450. And output is 10023004. So here this 0 is duplicated twice, so 2 shifted here. Now after 2 3 again one more 0, so here 0 0, and now this 4 will come here, and after that no more spaces, so this is the output. Now this is another example, 1 2 3, there are no zeros, so we will just return 1 2 3. And the constants are the array length should be less than equal to 10 to the power 4 and array of I, so it is a single digit starting from 0 to 9. Now whatever we discussed during our dry run, we will just follow that. So as per our algorithm, we will count the number of zeros. So first let's get the length of the array. Now count number of zeros. Count zeros is a variable, so here let's say it's 0. So here what we are doing is, if the array content is 0, we are just incrementing the count zeros value. We were creating 3 extra boxes in the first example because there were 3 zeros in that and we had to duplicate it 3 times. So we counted the number of zeros here, so those many imaginary boxes to be created. So the imaginary complete array length should be length of the array so far plus the number of zeros. So if the length is suppose 2 and there is 1 0, so after duplicating it there will be 3 length. that is 2 plus 1 for the duplicate. So here the imaginary length is current array length plus number of zeros. Imaginary length is a variable here and plus count zeros. Now after creating the imaginary boxes, we were starting from right to left, that is from end of the array to start of the array. So that's what we will do now. Shift from backward. So I was starting from the real end, that is n minus 1 position. So if the length of the array is 3, then I was starting from 2 because 0, 1, 2. So second index I will be starting from. So I starts from the real end and j was starting from the imaginary array end. So imaginary array length is this one. So j will be starting from this imaginary length minus 1, since our index will be that length minus 1. So j starts from imaginary length minus 1. So now let's declare same. So I comma j equal to n minus 1 and imaginary length minus 1. Now we have to start from right to left. So our edge or the end of the loop should be when I reaches 0, because after that it will be array out of bound because I will become minus 1. So we have to stop there when I becomes 0. So while I greater than equal to 0, we have to run the loop till then. Now we have two conditions: if the element is 0 or the element is non-zero. So if the element is non-zero, we were just copying the data from array of I to the array of j. So that's what we will do first. So here we were checking array of I not equal to 0. That means it is non-zero, but we were only copying because this is the imaginary boxes. What we saw in our example, the red colored boxes. So in that, we cannot copy anything to that because that does not actually exist. So we have to check if this j is within the array bound. So we can just check if j is less than n, then only we can copy everything. And we were decrementing j and I no matter what. Like no matter what means here whenever we were checking if it is a non-zero or 0, we were decrementing in both the cases, right? So even though it was out of bound, like j was in the imaginary boxes, still we have to decrement so that it will reach the within bound of the array. So here I will be decrementing by 1 and j will be decrementing by 1 as well, since it's a non-zero element. Now for the elements which is 0, what we need to do? We have to duplicate it in the j position and j minus 1 position. So let's just write that what we have to do. So I move backward by 1 and j move backward by 2. Now we have to check if this j is within the bound, because otherwise we cannot exactly put the 0 in it. So we have to check again the bound range. So if j less than n and j should be greater than 0 as well. Suppose j reaches minus 1, then we cannot do anything with it. It will give array bound error. So we have to check for the lower bound as well as upper bound. Then make it to 0. Now we will decrement it once first. So after this decrementing by 1, we will just check again if the shifted position is within the bounds. That is for safer range, so that we don't fail anywhere in the edge cases. So we decremented j twice. Now we will just decrement I as well. Now this is our entire code. So whatever we discussed in our dry run, we just counted number of zeros. Then we created the imaginary length, which will be current length of the array plus the number of zeros present. Then I will start from the real end, j will start from the imaginary end. Now we just defined that, and then we looked through the array till we reached I greater than equal to 0. And we just check the conditions for each element if it is 0 or non-zero. So when it is a non-zero element, we are just checking if j is within the bound. Then we will just copy array of I to array of j and will decrement I and j by 1. And if it is a 0, then we were copying the 0 at j and j minus 1 position and I was moving backward by 1 and j moving backward by 2. So before doing this, we were just checking if the j is within the bound. So both lower and upper bound we are checking, and if it is within the range, we made it to 0, and we were decrementing by 1 first. Then we were checking the range again, so that it does not give us any kind of error while going through any of the input array given. So after decrementing j twice, we were decrementing I once as well, and here it is written not to return anything. So this is our array in place modified, because we didn't create any other array, we just modified everything in the array itself. Like here we were just copying the element from I to j, and here we are just making the jth index to 0. So everything is done in place, we didn't create any new array, so we don't have to return anything. We'll just now run it and see the result by ourselves. So all the test cases passed. Now let's submit it. So it is submitted successfully. So let's see the time and space complexity here. So we are going through the array once, because we are just looping from right to left and going once till it reaches 0. So that means that time complexity is O of n and no extra spaces. So space complexity is O of 1. I hope you are able to understand what we coded here after we went through the dry run, because it is exactly the same what we did in the dry run, and we just wrote it into a code, and it completed successfully as well. So thank you for being with me so far. Let's move back to the slide. Let's quickly recap what we have learned. Our first instinct was to move forward and duplicate zeros, but that approach failed because inserting or replacing elements while iterating forward caused us to skip or overwrite data. Then we discovered the smarter way, the reverse approach, by planning space in advance and moving backward with 2 pointers. We duplicated zeros safely without changing the array's size. I read each element from the end, while j wrote elements and extra zeros in their correct positions. When the array started with zeros, the logic still held strong, gracefully ignoring duplicates that fell outside the valid range. No extra arrays, no chaos, just clean, calm, in place logic. So now you not only know how to duplicate zeros, but also why the reverse approach works beautifully in both regular and edge case scenarios. That's professional problem solving, clear, efficient, and confident. Let's look at both approaches side by side. The forward approach felt simple at first, but it failed because we tried to insert or replace elements while the array was still shifting beneath us. Each move caused something to go missing, and our logic quickly fell apart. Now the reverse approach. It's calmer, smarter, and safer. Instead of forcing changes, we plan space ahead, move backward, and place each element exactly where it belongs. That's the real difference. Forward forces change, reverse flows with the structure. Calm coding is not about speed, it's about clarity. You think ahead, you move with intention, and you let logic lead the way. And that's the calm power of thinking in reverse. When you stop fighting the array and start flowing with its logic, even complex problems become simple and smooth. Forward fails because it reacts. Reverse succeeds because it reasons. So remember, calm coders don't fight arrays, they flow backward. If you enjoyed learning this way, stay tuned for more calm, clear explanations on coding and algorithms. Every concept becomes easier when you slow down and understand it deeply. Thanks for watching, and I will see you in the next one.